The stars are the universe's punctuation marks. The real story is written in the dark. Everything you see, every planet and galaxy, is less than 5% of what actually exists. The cosmos is filled with particles and forces we cannot see, a hidden architecture holding reality together. By the end of this journey, you will understand the 30 most compelling theories for what that dark universe is made of. We will explore ghostly particles that pass through you by the trillions, black holes born in the first second of time, and forces that could rewrite gravity itself. What do you think is waiting for us in the dark? The first name on every detective's list is the WIMP. For decades, this has been the prime suspect in the case of the missing universe. WIMP stands for Weakly Interacting Massive Particle, and that name tells you almost everything you need to know. Imagine a particle with the mass of a heavy atom, perhaps 100 times heavier than a proton. But despite its heft, it is profoundly antisocial. It feels gravity, which is how it sculpts galaxies, and it feels the weak nuclear force, the same force behind radioactive decay. But it ignores light entirely. It does not absorb light, reflect light, or emit light. 1 trillion of these particles could be streaming through your body every second, and you would never know. They are cosmic ghosts, massive yet nearly intangible. This elegant idea did not come from nowhere. It emerged from one of the most beautiful frameworks in theoretical physics called supersymmetry. This theory proposes a profound symmetry in nature, suggesting that for every known particle we have catalogued, there exists a hidden, heavier partner. The electron has a selectron, the quark has a squark. This mathematical elegance solved several major puzzles in physics at once, and within this menagerie of new particles, theorists found a perfect candidate for dark matter. A stable, neutral particle that would have been forged in the fiery first moments of the Big Bang, in just the right abundance to account for all the dark matter we see today. This perfect alignment was so compelling, it was called the WIMP miracle. The hunt began in earnest. To catch a ghost, you need extreme silence. Laboratories were built deep underground, within mountains or old mines, shielded by a mile of solid rock from the constant rain of cosmic rays that would drown out any faint signal. The most sensitive experiments, with names like Xeno-NNT and LUX Zeppelin, are marvels of engineering. They use vats of ultra-pure liquid xenon, kept in darkness and chilled to extreme temperatures. The idea is to wait patiently for the once-in-a-blue-moon event where a passing WIMP bumps into the nucleus of a xenon atom. That tiny jiggle would create a flash of light and a puff of electrical charge, a signature that scientists could, in theory, spot. For over 30 years, these detectors have listened. They have grown larger, purer, and more sensitive with each generation, pushing the limits of what is technologically possible. And what have they heard? A profound and deepening silence, not a single confirmed bump. The parameter space where WIMP was supposed to live has been systematically carved away, ruled out by experiment after experiment. The once shining WIMP miracle has slowly dimmed into what many now call the WIMP crisis. It is a sobering reminder that the universe does not owe us easy answers. The prime suspect has a solid alibi, and the case must widen. The silence from those underground laboratories left a vacuum, and nature, as it always does, abhors a vacuum. Into that quiet stepped a very different kind of suspect, one so light and strange it seemed to come from a different playbook entirely. Meet the action. If the WIMP was a heavyweight bruiser, the action is a featherweight phantom, a whisper from the quantum realm. Its origin story is not one of missing mass, but of a profound and beautiful symmetry that should have been broken. Physicists call it the strong CP problem. In the equations governing the strong nuclear force, the glue that holds atomic nuclei together, there is a term that allows for a certain kind of asymmetry. This term, if it were large, would make neutrons behave as if they had a tiny, separate positive and negative end, like a microscopic bar magnet. This electric dipole moment would be measurable. The puzzle is this: after decades of searching, the neutron shows no such asymmetry. It is perfectly, mysteriously symmetric. The numbers in the equations suggest it should be there, but the universe says it is not. Why, in the late 1970s, physicists Roberto Pexi and Helen Quinn proposed an elegant fix. They suggested a new, fundamental symmetry that nature respects, one that dynamically cancels out that problematic term. And as a consequence of this new symmetry, a new particle must exist. Frank Wilczek named it the action, after a brand of laundry detergent, because it cleaned up a messy problem. The action would be astonishingly light, perhaps billions of times lighter than an electron, and incredibly shy. It would interact so weakly with normal matter that it makes the WIMP look downright gregarious. But here is the beautiful twist: this particle, invented to solve a deep puzzle in particle physics, turned out to be a perfect candidate for dark matter. In the hot, early universe, these actions would have been produced in enormous numbers, not as individual particles zipping around, but as a coherent, oscillating field that fills all of space. Think of it not as a swarm of invisible bees, but as a vast, silent ocean wave frozen into the fabric of reality, its subtle undulations providing the gravitational scaffolding for galaxies. This dual role is what makes the action a physicist's dream. One elegant idea solves two of the universe's greatest mysteries. Hunting it requires a completely different strategy. You do not look for a nuclear bump in a vat of xenon. You look for a conversion. In the presence of an incredibly strong magnetic field, theory predicts that an action could sometimes transform into a very specific, faint microwave photon. The Action Dark Matter Experiment, ADMX, is essentially a high-tech radio receiver inside a powerful magnet, cooled to near absolute zero to eliminate noise. It is tuning through the frequencies, listening for the faintest whisper of a note from this cosmic field converting into light. It is a search for a ghostly signal in a sea of silence, a testament to human ingenuity chasing an idea born from mathematical beauty. The action reminds us that the answer to the dark universe might not be a heavier version of what we know, but something fundamentally different, something woven into the very symmetries of reality itself. The search for actions is a quest for cosmic harmony, a whisper from a perfectly tuned universe. But what if the dark matter is not a product of beautiful symmetry, but a family secret hidden within a particle we already know? Enter the sterile neutrino, the mysterious, heavier cousin of one of the universe's most elusive known particles. To understand this suspect, we must first meet its famous family. Standard neutrinos are the ultimate minimalists. Trillions pass through you every second from the sun, born in the fiery hearts of stars and in the cataclysmic explosions of supernova. They are almost massless, electrically neutral, and they only deign to interact via the weak nuclear force and gravity. They come in three known types or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. And they have a strange habit of shape shifting as they travel, a phenomenon called oscillation, where one flavor morphs into another. This proved they have mass, a tiny revelation that won the Nobel Prize. But their story has some puzzling gaps. Certain experiments have recorded more oscillations than the three-flavor model can easily explain. It is as if a shadow is dancing just outside the spotlight. This is where the sterile neutrino enters the stage. Theorists propose a fourth flavor, a heavier sibling that is even more aloof. It would not interact via the weak force at all, nor the strong force, nor electromagnetism. Its only connection to our world would be through gravity and through its ability to mix with or oscillate into its three ordinary cousins. This total lack of other interactions is what makes it sterile. It is a ghost of a ghost. The implications are profound. First, this heavier, sterile neutrino could neatly explain those anomalous oscillation patterns, the shadow in the data. Second, and more tantalizing for our dark matter hunt, it could decay. If a sterile neutrino is unstable, its decay might produce a very specific signature, a faint spike of X-ray light at a precise energy. Astronomers have, in fact, detected an unexplained X-ray emission line from the hearts of galaxy clusters and from the nearby Andromeda galaxy. This line has no clear origin in known atomic physics, and it glows exactly where dark matter is thought to be densest. It is a cosmic clue written in X-rays, and the sterile neutrino is a prime suspect for the author. But this particle would not just be dark matter, it would be a specific kind called warm dark matter. Cold dark matter, like the classic WIMP, moves slowly, allowing it to clump tightly and form the seeds for all cosmic structure. Warm dark matter, like a heavier sterile neutrino, would have been born with more speed, streaming freely in the early universe. This streaming effect would smooth out small-scale clumps. It would predict fewer small satellite galaxies orbiting large ones like the Milky Way, a potential match for observations that have long puzzled astronomers. The hunt is on at both the smallest and largest scales. Particle accelerators like Fermilab are meticulously searching for the telltale deficit of neutrinos that would signal their oscillation into an invisible, sterile state. Meanwhile, space telescopes are scrutinizing the X-ray sky, mapping the mysterious emission line to see if its distribution truly follows the predicted gravitational footprint of dark matter. The sterile neutrino represents a compelling middle path, a bridge between the known and the unknown. It suggests the answer might not be an entirely new kingdom of particles, but a hidden chamber in a house we have already begun to explore. Yet for every theory that reaches into the quantum unknown, there is a simpler, more grounded question. What if the dark matter is not exotic at all? What if it is simply the stuff we know, hiding in the darkest corners of the cosmos? This brings us to our fourth theory, macho, an idea that forces us to look not for new physics, but for old matter in new guises. Macho stands for Massive Astrophysical Compact Halo Object. These are not particles, they are objects. They are made of the same ordinary protons and neutrons that build stars and planets and us, but they have gone dark. Imagine a universe littered with the ghosts of dead stars, black holes, the ultimate gravitational pits, neutron stars, city-sized spheres of crushed atomic nuclei. Failed stars known as brown dwarfs, too small to ignite. Even rogue planets cast adrift from their solar systems to wander the interstellar void. These are all macho. They emit little to no light, but their mass bends spacetime. If enough of them drifted in the vast halos surrounding galaxies, they could, in principle, explain the missing gravitational pull. Hunting them required a different kind of astronomy, one based on a cosmic alignment called gravitational microlensing. The principle is elegant. If a dark, compact object like a black hole passes directly between us and a distant background star, its gravity will act like a lens. It warps the fabric of space, bending and focusing the star's light rays toward us. For a brief period, that background star will not just brighten, it will brighten in a very specific, symmetric way, a sharp rise to a peak followed by an identical decline. The duration of the brightening tells you the mass of the invisible lens. It is a fleeting cosmic flash, a signature written in starlight by an unseen passerby. For years, projects like Eros and Ogle monitored millions of stars in the Magellanic Clouds, our galactic neighbors, waiting for these telltale flashes. They found some, but the numbers were devastatingly low. The census of macho revealed only a tiny fraction of the dark matter needed. Ordinary matter, even in its most hidden, compact forms, could only account for a small percentage of the gravitational mystery. The macho hypothesis, in its original form, was ruled out, but a fascinating subplot has recently emerged from its ashes. What if some of these compact objects are not the corpses of dead stars, but were born in the first chaotic instants after the Big Bang? These would be primordial black holes, not forged in stellar collapse, but in the intense density fluctuations of the infant universe. They could span a vast range of masses, from asteroids sized to many times the mass of our Sun. This revives the macho idea with a twist, suggesting a population of ancient black holes woven into the cosmic fabric from the very beginning. While they cannot be all the dark matter, they could be a part of it, a shadowy component of the dark sector. The search continues with new tools, like the subtle distortions they cause in the light of entire galaxies. The story of Macho is a crucial lesson in scientific humility. It reminds us that before inventing new particles, we must first exhaust the possibilities of the old. And sometimes, in ruling out the simple answer, we uncover a doorway to something even more profound. The Macho census left a void, but from that void a more ancient possibility emerges. Primordial black holes are not the ghosts of dead stars. They are fossils from the universe's birth, potential relics from the first chaotic fraction of a second after the Big Bang. To understand them, you must picture a cosmos that is not smooth, but seething with violent quantum fluctuations. In that unimaginable density, a region just slightly denser than its surroundings could have collapsed directly under its own gravity, bypassing the need for a star entirely. It would pinch off from the fabric of spacetime itself, becoming a black hole. The scale of this process is mind-bending. These black holes could have formed with almost any mass, from something as light as a small asteroid to something heavier than 1,000 suns. This range is their greatest asset and their deepest mystery. They slip through the net cast by the Macho searchers because those surveys were tuned to find objects roughly the mass of a star. A primordial black hole the size of a mountain would cause a microlensing flash too brief to see. One as heavy as a globular cluster would cause a lensing event too long and slow to recognize. They exist in the observational blind spots, but cosmology has other ways to hunt. The cosmic microwave background, that ancient afterglow of the Big Bang, is a meticulous record. If vast numbers of primordial black holes were evaporating in the early universe, they would have injected energy, distorting that pristine radiation in ways we do not observe. This places tight limits on how many small ones could exist. Then there are the gravitational waves. When the LIGO Observatory first heard the chirp of two black holes merging, a thrilling question arose. Were these the long-predicted stellar remnants, or could they have been primordial? The masses of some of those detected black holes were curiously high, hinting at an origin that predates stars. Furthermore, if the dark matter halo of our galaxy were swarming with asteroid-mass primordial black holes, we should occasionally see stars briefly twinkle as one passes in front. Surveys like the Subaru Hyper Subprime CAM have looked for these instant twinkles and found nothing, constraining this population too. Yet the most compelling role for these ancient objects may be as seeds. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole weighing millions or even billions of suns. How did they get so big so fast? It is a cosmic timing problem. Primordial black holes provide a head start. A heavy seed born in the first second would have 13.8 billion years to gorge on gas and stars and merge with others, growing into the behemoths we see today. They would be the gravitational anchors around which the first stars and galaxies coalesced. So while they may not be all the dark matter, primordial black holes represent a breathtaking synthesis. They are a bridge between the infinitesimal quantum jitters of the beginning and the largest structures in the cosmos, a reminder that the answer to our darkest mystery might be written in the geometry of spacetime itself. That ancient geometry of spacetime is one kind of hidden structure, but what if the dark sector is not a collection of isolated particles or silent black holes, but a bustling, interactive society all its own? This brings us to SIMP, a theory that flips the script on the classic dark matter narrative. While WIMP are defined by their weakness, SIMP are defined by their strength. The acronym stands for Strongly Interacting Massive Particle. The key difference is right there in the name. These particles would not just ignore normal matter, they would actively talk to each other. They would have a strong force, a dark force that operates only within their own hidden realm. Imagine a vast, invisible city superimposed over our own, where dark matter particles constantly collide, scatter, and exchange energy, completely oblivious to the world of light happening around them. This is not a ghostly haze, it is a dynamic, interactive fluid of darkness. Why would theorists invent such a thing? Because our maps of the cosmos have some persistent, small-scale wrinkles. The most famous is called the cusp core problem. When cosmologists run ultra-detailed supercomputer simulations of how cold, collisionless dark matter should clump under gravity, they get a very specific prediction. The centers of galaxies, especially small dwarf galaxies, should be extremely dense, rising to a sharp peak or cusp of dark matter. But when astronomers measure the rotation of stars in real dwarf galaxies, they find something else. The centers seem smoothed out like a soft core instead of a sharp spike. It is as if something is stirring the pot, preventing the dark matter from piling up too densely in the middle. SIMP offer a beautifully simple solution. If dark matter particles strongly interact with each other, they do not just fall neatly into a gravitational well. They collide and scatter, transferring energy. This creates a kind of internal pressure, like the heat in a gas, that resists being compressed into an overly dense cusp. The dark matter halo becomes puffier, more like a fluffy cloud than a sharp spike, neatly matching the observed cores of dwarf galaxies. This self-interaction also changes the story of how dark matter survived from the Big Bang to today. In the early, searingly hot universe, these SIMP would have been in constant, vigorous collision, maintaining what physicists call a thermal bath. Their abundance would not be set by a freeze-out from normal matter, as with WIMP, but by a freeze-out from their own interactions. As the universe expanded and cooled, they would suddenly find themselves too far apart to keep colliding, and their numbers would become fixed. This is a different pathway to the correct relic density, one that operates entirely within the dark sector. So how do you hunt for something that only interacts with itself? You look for the sociological effects of the crowd, not the fingerprint of an individual. You study the shapes of the smallest, most dark matter-dominated galaxies, searching for the telltale signs of that internal pressure. You look for galaxy clusters that have recently collided. In a famous system known as the bullet cluster, the hot gas from two colliding clusters slams together and slows down, but the dark matter, inferred from its gravitational lensing effect, seems to sail right through. If dark matter were strongly self-interacting, even a little, we might expect to see it lag behind or spread out more than it does. The current observations slightly favor the non-interacting model, but the door is not closed. Even more subtly, the constant early universe collisions of SIMP would have injected just a bit more heat into the cosmic microwave background, potentially leaving a faint statistical imprint on its polarization patterns. Future observatories might one day detect that whisper from the dark sector's fiery youth. The SIMP hypothesis is a powerful reminder that dark matter does not have to be inert. It can have a rich, complex inner life, with forces and interactions that sculpt the universe in ways gravity alone cannot explain. The idea of a self-interacting dark fluid is compelling, but it still leaves a fundamental force out of the picture. Gravity itself is the architect of the cosmos, the curve in space-time that guides everything. Yet in our standard model of particles, it is the only force without a known carrier. This gap points us toward a theory that is perhaps the most ambitious synthesis of all: supergravity, and with it, a dark matter candidate of profound elegance called the gravitino. To understand this, we must take the elegant symmetry of supersymmetry one step further. Supersymmetry gave every particle a hidden partner. Supergravity asks what happens when you weave Einstein's theory of gravity into that same symmetric framework. The result is a prediction. Just as the photon is the carrier of the electromagnetic force, physicists hypothesize a particle called the graviton to be the carrier of gravity. In supergravity, this hypothetical graviton must also have a superpartner. That partner is the gravitino. If the graviton is the quantum of space-time curvature, the gravitino is a staggering fusion. It is a particle that carries both the properties of a force carrier and the properties of matter, a hybrid of the highest order, and it comes with a breathtaking resume for dark matter. The gravitino would be incredibly massive, likely thousands of times heavier than a proton, and profoundly stable. Most importantly, its preferred interaction is gravity itself. It would ignore the electromagnetic and strong forces entirely, and its interactions via the weak force would be vanishingly small. This makes it the ultimate ghost, a particle that speaks only the language of space-time, weaving the gravitational tapestry of the universe while remaining utterly invisible within it. There is, however, a cosmic balancing act of exquisite delicacy. In the hot, dense early universe, gravitinos would have been produced in furious collisions. If too many were created, their sheer collective mass would have caused the cosmos to collapse back on itself long ago. The universe would have overclosed, ending in a swift gravitational crunch. The fact that we are here in an expanding universe 13.8 billion years old means this did not happen, so theorists must walk a tightrope. Models carefully tune the early production of gravitinos, often through two main pathways. In one, they are forged from the thermal soup itself through the scattering of other particles, but in just the right, limited numbers. In another, more compelling scenario, they are not produced directly, but are the final, stable relics from the decay of other, heavier supersymmetric particles. Imagine a hidden, heavier particle from the supersymmetric family decaying, like a cosmic clockwork unwinding, and at the end of its chain, it leaves behind a single, stable gravitino as its ash. This process naturally yields the precise, sparse abundance needed to account for dark matter without dooming the cosmos. This is why the gravitino is so captivating to theorists. It does not just propose a new particle, it tightly binds the mystery of dark matter to humanity's greatest theoretical quest, the search for a quantum theory of gravity. Finding evidence for a gravitino would be a direct signal that supersymmetry and gravity are unified, a glimpse into the deepest layer of reality's code. The hunt, however, is phenomenally difficult. You cannot build a detector for something that only feels gravity. The search is indirect, played out in the careful predictions of cosmology and in the hopes of spotting other supersymmetric particles at machines like the Large Hadron Collider. If those heavier partners are found and their decay patterns show missing energy that could be carried off by a gravitino, it would be a monumental clue. The gravitino represents a grand vision where the solution to the dark universe is not an add-on, but a fundamental piece of the puzzle that unites everything we see with the force that holds it all together. Gravity and light are the two great forces that sculpt our cosmic experience, yet for a century they have stubbornly resisted being unified in a single, elegant framework. One of the earliest and most beautiful attempts to do just that came from a mathematician named Theodore Kaluza, and it leads us to a dark matter candidate born from the very geometry of reality. Kaluza's radical idea was to take Einstein's equations of general relativity, which describe gravity as the curvature of four-dimensional spacetime, and simply write them in 5 dimensions. The result was astonishing. The extra terms in the equations perfectly described Maxwell's theory of electromagnetism. It was as if light was not a separate force, but a subtle vibration in a hidden 5th dimension. To explain why we do not perceive this dimension, physicist Oscar Klein suggested it must be curled up or compactified on a scale so tiny. perhaps a billion times smaller than an atom, that it is utterly invisible to our senses. Imagine a garden hose. From a great distance it looks like a simple one-dimensional line, but up close you see it has a circular cross-section, a second dimension curled into a tiny loop. Our universe in this view could be like that hose, with 4 large familiar dimensions and 1 or more incredibly small curled up ones. This Kaluza-Klein framework has profound implications for particles. In our flat, 4-dimensional perspective, a particle moving through a curled-up dimension would have its momentum quantized, appearing to us as discrete energy levels. The consequence is a tower of heavier partner particles for every known particle we have. For the photon, there would be a Kaluza-Klein photon. For the electron, a Kaluza-Klein electron. This is not supersymmetry, but a geometric necessity, and within this tower a prime candidate for dark matter emerges, the lightest Kaluza-Klein particle, or LKP. Typically, this is the first excited state of the photon, or perhaps another neutral particle. Crucially, it is stable. A symmetry of the extra-dimensional geometry, called momentum conservation in the 5th dimension, prevents it from decaying into ordinary particles. It is a relic frozen in from the early universe, with a mass set by the size of the hidden dimension. The smaller the curled-up dimension, the heavier the Kaluza-Klein particles. If this scale is about 1,000 times smaller than a proton, the LKP would have a mass perfect for a thermal relic, providing the right amount of dark matter today. Its interactions are a unique fingerprint. It would feel electromagnetism, but only in a higher dimensional sense, coupling to ordinary matter with a strength comparable to the weak force. This makes it detectable in principle, but its signature is distinct. In particle colliders like the Large Hadron Collider, the production of a pair of Kaluza-Klein particles would appear as a dramatic burst of missing energy as the stable LKPs escape the detector, carrying their momentum off into the hidden dimensions. More poetically, these particles could reveal themselves in the depths of space. If they make up the dark matter halo of our galaxy, they will occasionally annihilate with each other. That annihilation would not produce standard particle pairs, but a cascade that ultimately showers down into gamma rays, positrons, and antiprotons. Space telescopes have been searching for unexplained excesses in these cosmic rays, looking for a spectral line or a peculiar shape in the data that could be the death cry of 2 Kaluza-Klein particles meeting in the void. The Kaluza-Klein particle is a whisper from a more spacious cosmos. It suggests that the answer to our darkest mystery might not be a new ingredient, but a new direction, a hidden compact geometry whose vibrations give mass to the shadows. Hidden dimensions offer one kind of symmetry, but there is an even more profound possibility. The universe might be perfectly and literally mirrored. This is the theory of mirror matter, a concept so elegant it feels almost inevitable. What if for every particle in our world, every electron, every quark, every photon, there exists an exact duplicate, a mirror copy with the same mass and the same internal forces? These mirror particles would form mirror atoms, which could coalesce into mirror stars, mirror planets, and even mirror galaxies. They would have their own mirror light and mirror chemistry, a complete parallel universe made of shadow stuff. But here is the crucial twist. This mirror sector would not interact with ours via electromagnetism, or the strong force, or the weak force. Its only bridge to our reality would be gravity. A mirror galaxy could be sitting right on top of our Milky Way, its stars and planets seamlessly intermingled with ours, and we would never see it. We would only feel its collective gravitational pull, a perfect explanation for the dark matter halos we observe. It is not a halo of unknown particles, it is a halo of mirror stars. The implications are staggering to contemplate. This mirror universe would have its own cosmic history. Mirror hydrogen would fuse in the cores of mirror stars, shining with mirror light invisible to our eyes. those stars would eventually die, some exploding as mirror supernova cataclysms of pure gravity we might detect only as a burst of gravitational waves. Rocky mirror planets could form in mirror solar systems, and if mirror chemistry follows the same rules, the possibility of mirror life emerges. An entire biosphere of mirror organisms could exist right here on Earth, their mirror DNA and mirror cells completely oblivious to our sunlight, passing through our buildings and our bodies like ghosts. They would not be supernatural, they would simply be built from matter that talks to a different set of forces. Yet for this beautiful symmetry to work, it must be slightly broken. The mirror sector cannot be an exact twin in every way, or we would face a cosmological catastrophe. In the first few minutes after the Big Bang, the process known as Big Bang nucleosynthesis forged the first light elements, hydrogen, helium, and a trace of lithium. The amounts produced match the observed cosmic abundances with exquisite precision. But if a mirror sector with identical particles existed at exactly the same temperature as our own, it would have produced an equal amount of mirror hydrogen and mirror helium. This would double the total density of normal matter, throwing off those perfect predictions. The universe, it seems, allows for a mirror, but it must be a cooler mirror. Theorists suggest that in the earliest moments, the two sectors may have decoupled, with the mirror universe cooling down faster than our own. If it were, say, half the temperature, its contribution to the total density of normal matter during nucleosynthesis would be negligible, preserving the successful predictions we rely on. This temperature difference would also mean mirror stars burn differently and evolve on different timescales, making the parallel cosmos even more alien. The search for this shadow universe is a hunt for gravitational echoes and subtle asymmetries. If mirror matter accumulates here on Earth, it could form rare, exotic minerals with extraordinary density as mirror atomic nuclei packed together. Some experiments have searched for these strange, heavy rocks with no success yet. More promising might be the search for particles that are portals between the sectors, like the hypothetical mirror neutron, which could oscillate into an ordinary neutron and back. This could explain another lingering anomaly in particle physics. The mirror world theory is perhaps the ultimate expression of cosmic economy. It does not invent a handful of new particles, it replicates the entire known catalog, suggesting that the darkness we feel is not a void, but a reflection, a silent twin universe whose gravity is the only handshake it offers across the dimensional divide. But a mirror world, for all its elegance, is a kingdom of particles. What if the truth is not a collection of discrete things at all, but a single, continuous entity, a vibration in the very fabric of reality? We now cross a fundamental threshold from the realm of particles into the domain of waves. This is the theory of fuzzy dark matter, where the cosmos is not filled with invisible bullets, but with a silent, universe-spanning hum. The candidate is an action, but not just any action. It is an action pushed to an extreme so radical it ceases to behave like matter as we know it. Imagine an action billions of times lighter than the ones we discussed earlier, with a mass so tiny it is almost a property of empty space itself. At these inconceivably small masses, quantum mechanics does something extraordinary. It grants the particle a de Broglie wavelength, a measure of its quantum fuzziness, that stretches not across an atom but across an entire galaxy. A single particle is no longer a point, it is a diffuse cloud, a wave function as vast as a dwarf galaxy. Now multiply that by the countless trillions in the universe and they cease to be individuals. They merge into a single, coherent field, a vibrating fluid of quantum potential that fills every cubic inch of the cosmos. This is fuzzy dark matter. Its behavior is not governed by the collisions of billiard balls, but by the interference patterns of waves. Think of the dark matter halo of a small galaxy not as a swarm of bees, but as a standing wave in a vast, invisible ocean with peaks and troughs of density. This wave nature has a dramatic effect on cosmic structure. The smallest clumps of dark matter, those that would normally seed tiny satellite galaxies, are erased. The quantum pressure from the wave's inherent jitter smooths them out like surface tension on water, preventing very small ripples from forming. This could elegantly solve the missing satellites problem, the puzzling observation that our simulations predict hundreds of small dwarf galaxies around the Milky Way, but we only see a few dozen. Fuzzy dark matter says the smallest ones never got to form in the first place. The wave nature of the dark matter washed them away. This cosmic fluid would also have a unique texture. On scales smaller than its wavelength, it would exhibit intricate interference patterns, creating a subtle, frothy structure within galaxy halos. This could influence how the first stars formed, potentially leaving an imprint in the faint, ancient light of the early universe. Detecting such a field requires listening for its faintest vibrations. One promising method looks to the cosmos's natural lighthouses, pulsars. These rapidly spinning neutron stars emit beams of radio waves with the precision of atomic clocks. As gravitational waves from distant black hole mergers pass through, they stretch space-time and minutely alter the pulsar's rhythm. A universe-filling field of fuzzy dark matter would also create a background of ultra-low frequency waves, a gentle hum that would collectively nudge the spins of these pulsars in a correlated way. By monitoring networks of pulsars across the galaxy, astronomers are essentially building a galaxy-sized microphone, listening for the hum of this quantum sea. Another approach is statistical, mapping the distribution of millions of galaxies to search for the specific, wavy signature of interference patterns imprinted in the large-scale structure of the universe. Fuzzy dark matter challenges our deepest intuitions. It suggests the missing 95% of reality is not a thing, but a condition, a fundamental vibration of the vacuum whose gentle pressure holds the stars apart. That silent hum of fuzzy dark matter is one kind of cosmic pressure, but what if the dark sector has a more dynamic way to resist gravity's pull, a way that involves not just waves but actual conversations between its constituents? This leads us to a broader, more flexible idea: self-interacting dark matter. While SIMP are one specific model, SIDM is the entire genre. It proposes that dark matter particles do not just pass through each other like ghosts. They feel a new force, a dark force that operates only within their hidden realm. This force needs a carrier, much like the photon carries electromagnetism for us. Theorists call this the dark photon, a particle that would shuttle between dark matter particles, allowing them to push and pull on one another. This creates a hidden society with its own rules, its own physics, completely separate from our world of light. The consequences for galaxy shapes are profound. Picture a galaxy's dark matter halo not as a static, lumpy cloud, but as a bustling metropolis. Particles are constantly interacting, colliding, and exchanging energy through their dark force. This acts like a form of heat or pressure. Just as air in a balloon resists being squeezed, this self-interaction resists gravity's attempt to pack dark matter into an overly dense knot at the galaxy's center. It smooths out the sharp cusps predicted by cold, collisionless models into the soft cores astronomers actually observe in dwarf galaxies. It also makes the overall halo more spherical and puffy, especially in its inner regions, because the interactions redistribute energy, much like stirring a cup of coffee evens out the temperature. This is not a minor tweak, it's a fundamental shift in how dark matter behaves on the scale of individual galaxies. To test this, we look for cosmic accidents where the dark sector's sociology might be revealed. The most famous laboratory is the Bullet Cluster, the aftermath of a violent collision between two galaxy clusters. In that system, the hot, X-ray emitting gas, the normal matter, slammed together and slowed down dramatically. But the dark matter, mapped by its gravitational lensing effect, seemed to sail right through the collision, showing it does not interact with normal matter or with itself strongly enough to slow it down much. This was a landmark finding that ruled out dark matter being some form of obscure, sticky normal matter. But for SIDM, the story is more subtle. If the dark force is strong enough, we might expect to see the dark matter lag slightly behind the galaxies in such a collision, or to spread out into a broader, more diffuse cloud. In the bullet cluster, the dark matter and the galaxies are aligned, suggesting the interactions are not extremely strong. However, other cluster collisions show more puzzling features. Some appear to have dark matter that is offset from the galaxies, or shapes that are harder to explain without some form of internal friction. These are the tantalizing clues that keep the SIDM hypothesis alive and vigorously debated. The search continues in the detailed structures of the smallest, darkest galaxies we can find, where the effects of self-interaction should be most pronounced. It also continues in particle physics labs, where experiments are actively searching for the possible portal particle, the dark photon, which could occasionally have a vanishingly small connection to our own electromagnetism. Self-interacting dark matter transforms the mystery from a search for a single particle into the exploration of an entire hidden cosmos, a parallel reality with its own forces and interactions, whose gentle internal pressure helps sculpt the luminous galaxies we call home. The hum of a cosmic sea and the chatter of a dark society both assume a fundamental equality, but our own universe is built on a profound and lucky imbalance. Every star, every planet, you yourself, are here because of a single critical fact. In the first moments of creation, there was slightly more matter than antimatter. For every 10 billion antiquarks, there were 10 billion and 1 quarks. After the inevitable annihilation, that 1 in 10 billion surplus was all that remained to build everything we see. This is the Barrian asymmetry, and it begs a monumental question. What if dark matter owes its existence to the very same kind of cosmic favoritism? This is the theory of asymmetric dark matter. It proposes that the dark universe is not a symmetric sea of particles and antiparticles in perfect balance. Instead, like us, it is the relic of an ancient war where one side narrowly won. In the scorching dawn of time, a process, perhaps the same one that tilted the scales for us, also generated a tiny excess of dark matter particles over their antiparticles. They too would have engaged in total annihilation, wiping each other out in flashes of dark energy. But that slight excess, that 1 in a billion survivors, would be left behind, frozen into the expanding cosmos as the dark matter we detect today. The elegance is breathtaking. It directly links the two greatest material abundances in the universe, the density of visible atoms and the density of dark matter, suggesting they are two sides of the same coin, two outcomes of a single primordial event that broke the symmetry of creation. This is not a random numerical coincidence. It is a potential clue written into the foundation of everything. How could such a transfer happen? Theorists imagine a cosmic connection in the ultra-early universe, a fleeting interaction between the visible and dark sectors. Through some yet unknown particle or force, the asymmetry generated in our sector, the excess of quarks over antiquarks could have been communicated or transferred into the dark sector, seeding an excess of dark particles over dark antiparticles. They are not necessarily generated separately, but are linked by a shared history. In some models, this connecting particle decays, and in its decay, it obeys a rule that for every visible matter particle it produces, it must also produce a dark matter particle, locking their abundances together. This creates a powerful narrative where the darkness we feel is not an alien intruder, but a sibling born from the same unstable moment we were. If this is true, it leaves fingerprints we might one day find. One dramatic possibility involves neutron stars, those ultra-dense corpses of dead suns. If asymmetric dark matter particles accumulate in a neutron star over billions of years, drawn in by its immense gravity, they could eventually reach a critical density. At that point, they might trigger a catastrophic collapse, transforming the entire neutron star into a smaller, even denser black hole in a sudden, silent event. Astronomers could search for the disappearance of known pulsars or for the gravitational wave chirp of such a sudden, implosive transformation. On Earth, the hunt is more subtle but equally profound. The particles that mediated the transfer of asymmetry in the early universe might still exist, albeit rarely. They could manifest in experiments searching for impossibly rare particle decays that violate known symmetries, processes where, for example, a neutron might decay into invisible dark sector particles instead of a proton and electron. Observing such a decay would be a direct window into the mechanism that gave both light and dark their shape. Asymmetric dark matter reframes the entire mystery. It suggests the vast, invisible ocean holding galaxies together is not a separate entity, but our cosmic twin, a shadow born from the same fragile accident that made our own existence possible. A sibling universe needs a way to talk to itself. That conversation requires a messenger. Within the elegant framework of a dark sector, the most compelling candidate for that messenger is the dark photon. This is not a particle of darkness in the sense of shadow, but a force carrier, the dark equivalent of our own photon. Just as our photon mediates the electromagnetic force between charged particles like electrons, a dark photon would mediate a dark electromagnetic force between particles that carry a dark charge. This creates the possibility of a rich, complex dark chemistry with dark atoms, dark molecules, and dark light, all completely invisible to our eyes and instruments. The only reason we have any hope of detecting this hidden cosmos is a subtle, almost poetic loophole called kinetic mixing. In the quantum foam of empty space, it is theorized that our ordinary photon and the dark photon can, very rarely, oscillate into one another. They are not the same, but they share a faint, fundamental kinship. This tiny mixing would give any particle charged under the dark force an infinitesimally small, ordinary electric charge. It is the thinnest of threads connecting the two worlds. A dark matter particle could then interact with our matter not with the strength of the full electromagnetic force, but with a strength suppressed by a factor of 1 billion or 1 trillion. It is a ghostly touch, but it might be enough to leave a trace. The hunt for this spectral messenger spans 3 frontiers. First are the beam dump experiments. Here, physicists take a powerful particle beam, often electrons or protons, and slam it into a thick, dense wall of material. Most particles are stopped dead, creating a shower of known secondary particles. But if dark photons exist, they could be produced in that collision, and because they interact so weakly, they would sail straight through the wall, escaping the dump. In the shielded cavern beyond, sensitive detectors wait for the rare dark photon to decay into a pair of ordinary electrons or positrons, a telltale spark appearing from seemingly nothing. Experiments like NA64 at CERN are conducting this very search, looking for an unexpected excess of such events. The second frontier is one of exquisite precision. The electron has a property known as its magnetic moment, essentially the strength of its tiny internal magnet. Quantum electrodynamics allows us to calculate this value with mind-boggling accuracy to better than 1 part in 1 trillion. Any discrepancy between the theoretical prediction and the experimentally measured value could be a sign of new physics, including virtual dark photons popping in and out of existence in the quantum vacuum around the electron, subtly tweaking its magnetism. While recent measurements show remarkable agreement, even tighter constraints help narrow the territory where the dark photon could be hiding. The third frontier is the high-energy chaos of particle colliders. When protons are smashed together at nearly the speed of light, they can produce a cascade of exotic particles. Researchers meticulously sift through the debris, looking for events with significant missing energy and momentum, a signature that something invisible, like a dark photon, was created and carried that energy away unseen. Or they search for the invisible decay of known particles, like certain types of mesons, which might occasionally decay into a dark photon and something else, with the dark photon then escaping detection. Each non-discovery carves away another slice of possibility, guiding theorists toward the most viable models. This is not merely the search for a single particle. The dark photon is a key, a potential portal into a dark sector that could be as rich and varied as our own visible universe. Finding it would be the first step into a hidden cosmos, revealing that the darkness is not an empty void, but a structured, dynamic realm with its own laws, its own forces, and its own light that we are only beginning to sense. The dark photon offers a whisper of connection between our world and the hidden one. But what if the truth is even more austere, a form of darkness born from the pure geometry of creation itself, with no new forces at all? This is the realm of Planckian interacting dark matter. It is a theory of stark, breathtaking minimalism. Here, dark matter does not talk to itself, nor does it feel any of the standard model forces. Its only significant interaction in the early universe was with the inflaton itself, the mysterious field that caused space to expand exponentially in a fraction of a second during cosmic inflation. Imagine the inflaton as the engine of the Big Bang, a scalar field that stretched the universe from a quantum speck to a macroscopic cosmos in an instant. As this inflationary period ended, the inflaton field oscillated and decayed in a violent process called reheating, dumping its immense energy into the production of all the hot particles of the standard model. In this maelstrom, through purely gravitational interactions, dark matter was also forged. Its birth certificate was signed by gravity alone. This model makes a profound prediction about the mass of these particles. They would be unimaginably heavy around the Planck mass. The Planck mass is a fundamental scale in physics, derived from the constants of gravity and quantum mechanics. It is about the mass of a grain of dust, but concentrated into a single particle 22 micrograms, which is 10 to the 19 times heavier than a proton. At this scale, gravity becomes as strong as the other forces, and quantum gravity effects are paramount. These would be the ultimate individual dark matter candidates, incredibly sparse, but each one a mountain of mass on the quantum level. Their production mechanism is elegantly simple and inevitable in this framework. During reheating, the oscillating inflaton field can gravitationally produce pairs of these Planck mass particles directly from the energy of spacetime itself. Since they interact with nothing else, they never thermalize with the hot plasma of normal matter. They simply fall out of the soup cold and inert, their abundance frozen in by the expansion of the universe. The beauty of this idea is its economy. It requires no new forces, no complex dark sectors, no low-energy particles beyond the inflaton, which is already a necessary component of our best cosmological models. It ties the existence of dark matter directly to the most dramatic event in cosmic history, the inflationary Big Bang. Detecting such an isolated entity, however, is a monumental challenge. If they are stable, their only signal is their collective gravity. We would feel their pull in galactic halos, but distinguishing them from other dark matter candidates would be nearly impossible from rotation curves alone. The hope for a more active signature lies in the possibility that they are not perfectly stable. If these Planck mass particles can decay or annihilate with one another, the energy release would be cataclysmic. A single decay would unleash a particle with energy equivalent to a kilogram of TNT, but concentrated into a single, ultra-high-energy cosmic ray. These would be the most energetic particles in the universe, far beyond what any human-made accelerator could produce. Observatories like the Pierre Auger Observatory scan the skies for such rare, mysterious events, searching for the fingerprints of decaying dark matter in the cosmic ray spectrum. While no definitive signal has been found, the search itself probes the most extreme frontiers of particle physics and cosmology. Planckian interacting dark matter represents a philosophical extreme. It suggests the shadows holding galaxies together are not a bustling hidden society, but ancient solitary monuments, relics from the first moment when gravity itself was born, carved from the raw geometry of inflation and left to drift through eternity. These solitary Planck mass relics are one extreme, but the dark universe might be filled with structures that are both massive and strangely diffuse. Cue balls propose a form of dark matter that is not a fundamental particle nor a black hole, but a stable, macroscopic knot in the fabric of a quantum field. Think of the universe's underlying fields not as perfectly smooth, but as a kind of cosmic gelatin. Under the right conditions, a bubble can form within that gelatin, a region where the field is trapped in a different state than the surrounding space. This bubble is a cue ball. The Q stands for a conserved charge like baryon number that gets locked inside. This charge stabilizes the bubble, preventing it from dissolving away. The result is a soliton, a solitary, self-sustaining wave that can behave like a single, gigantic particle. A single cue ball could weigh anywhere from a microscopic speck to more than an entire planet, all while being fundamentally a coherent object, a single excitation of a field stretching across a vast volume. Their formation is a story of cosmic cooling. In the searing heat of the early universe, fields were symmetric and uniform. As everything expanded and cooled, these fields underwent phase transitions like water freezing into ice. But just as bubbles form when water boils, the transition might not happen perfectly evenly everywhere. Patches of the field could get stuck in the old high-energy state, surrounded by the new lower-energy vacuum. These trapped patches are the seeds of cue balls, fossilized bubbles from a more energetic age. Because they are stabilized by their internal charge, they can be incredibly long-lived, persisting from those first moments all the way to the present day, drifting through galactic halos. Detecting such an exotic object requires looking for its passage through our world. If a planet-mass cue ball passed through the Earth, its immense gravity would compress and stretch the planet's interior as it approached, then release it as it departed. This could trigger a worldwide, simultaneous seismic event, a deep, resonant ring of the entire planet with no epicenter, a signature no ordinary earthquake or impact could produce. Sensitive networks of seismometers are, in principle, listening for such an impossible tremor. On a smaller scale, a microscopic cue ball, still far denser than any normal matter, might zip through the Earth and leave a trail of atomic disruption in its wake. Scientists have examined ancient mica crystals, minerals that preserve damage tracks over geological timescales, searching for the unique, dense trails that only a nuclear-scale object moving at cosmic speeds could create. Perhaps the most elegant search uses the stars themselves. A cue ball drifting in front of a distant star would act as a gravitational lens, bending and magnifying its light. Because a cue ball is an extended object, not a point like a black hole, it would produce a distinctive lensing signature, a smooth, symmetric brightening and fading of the star's light over days or weeks. Surveys that monitor millions of stars for microlensing events like Ogle could one day catch the telltale curve of a cue ball's passage. This theory utterly transforms the picture. Dark matter becomes not a swarm of invisible points, but a sparse collection of massive, classical knots, quantum bubbles floating in the dark, each one a relic of the universe's first and most dramatic change of state. The universe remembers its first moments in the structures we see today. A sterile neutrino with a mass measured in kilo-electronvolts offers a specific, powerful memory, warmth. This is not cold, sluggish dark matter, but warm dark matter, a population of particles born with enough speed to fundamentally reshape the cosmos on its smallest scales. The key difference is kinetic energy. In the first microseconds, these sterile neutrinos would have been relativistic, zipping through the primordial plasma at a significant fraction of light speed. This velocity is a form of pressure, and it acts like a cosmic iron, smoothing out wrinkles below a certain size. tiny density fluctuations, the seeds for the smallest galaxies, get washed away by this streaming motion. The result is a universe where large-scale structure, the vast cosmic web of filaments and clusters, forms just as we observe, but the abundance of the tiniest galactic building blocks is sharply suppressed. This directly addresses one of the most persistent puzzles in modern cosmology, the missing satellites problem. Supercomputer simulations that assume cold, slow-moving dark matter predict that hundreds of small dwarf galaxies should be orbiting the Milky Way, held in the grip of its dark matter halo. Our telescopes, however, have only found a few dozen. Warm dark matter provides an elegant explanation. The smallest, earliest clumps simply never had a chance to form. The warm particles streamed right out of them, preventing the gravitational collapse needed to ignite the first stars in those tiny halos. A sterile neutrino with a mass around 7 kilo-electronvolts fits this role perfectly. It is heavy enough to be non-relativistic by the time large structures form, yet light enough to have retained that crucial smoothing power in the universe's youth. Its decay offers a potential beacon. If these sterile neutrinos are unstable, they could slowly decay into an ordinary active neutrino and a photon. The energy of that photon would be precisely half the sterile neutrino's mass, appearing as a faint monochromatic X-ray line. For a 7 kilo-electronvolt particle, this line would appear at about 3.5 kilo-electronvolts. Intriguingly, astronomers have detected an unexplained X-ray emission line at exactly that energy from the Perseus galaxy cluster and other massive objects. While the signal remains controversial and could be explained by mundane atomic processes, its tantalizing alignment keeps the hunt alive. The impact of warm dark matter extends beyond dwarf galaxy counts. By suppressing small-scale structure, it would delay the formation of the very first stars. In a cold dark matter universe, stars can ignite in incredibly small, dense halos quite early. With warm dark matter, the first luminous objects would need to wait for larger halos to assemble, potentially shifting the cosmic dawn later by tens of millions of years. This delay could leave an imprint on the faint radio signals from the era of reionization, a frontier being probed by ambitious new telescopes. The choice between cold and warm dark matter is not merely academic. It is a choice between two different histories of cosmic structure, two narratives of how the darkness sculpted the light. The sterile neutrino, sitting in that Kiwi sweet spot, offers a compellingly minimal bridge between the particle world and the grand architecture of the cosmos, suggesting the dark universe might have been born with a little more heat and a little less clutter than we once thought. Gravity is the oldest known force, the silent hand that guides the cosmos, yet for all its power it might be incomplete. The 17th theory on our list is the most radical departure of all because it asks a shocking question: what if there is no dark matter at all? What if instead the laws of gravity themselves are wrong? This is the core of modified Newtonian dynamics, or MUND. It is not a search for a hidden particle, but a revision of the fundamental script of the universe. The idea was born from a simple, elegant observation. In the 1980s, physicist Mordechai Milgrom noticed something peculiar about galaxy rotation curves. The discrepancy between the predicted and observed speeds always became significant in the same environment: the sparse outer regions of galaxies, where the gravitational pull from the visible stars becomes extraordinarily weak. It was not about distance, but about the absolute strength of the acceleration. Milgrom proposed a breathtakingly simple fix. He suggested that Newton's second law, F equals ma, which we all learn in school, changes its form at extremely low accelerations. Below a critical threshold, a value so tiny it is 100 billion times weaker than the gravity you feel standing on Earth. The relationship between force and acceleration becomes different. In this regime, a tiny amount of force produces a much larger acceleration than Newton or Einstein would predict. The implications are profound. Apply this modified law to a spiral galaxy, and the math changes completely. The stars in the outer disk, feeling these ultra-weak accelerations, no longer need the gravitational glue of a vast dark matter halo to keep them orbiting so quickly. The modified law itself provides the extra kick. With a single new constant, man can accurately predict the rotation curves of a stunning variety of galaxies, from tiny dwarfs to massive ellipticals, often with more success than the standard dark matter model. It is a triumph of empirical fitting, a simple rule that describes a vast array of data with startling precision. For its proponents, this is Occam's razor in action. The simplest explanation is that we have misunderstood gravity, not that we have missed 95% of the universe's content. But a theory that works so beautifully on one scale must hold up on all others, and here man faces its greatest trials. The first is a cosmic collision. In the bullet cluster, two galaxy clusters have slammed together. The visible gas, hot and sticky, was slowed by the impact and sits in the center, but the mass mapped by gravitational lensing is offset, having sailed ahead with the galaxies. In the standard view, this is perfect evidence for dark matter, a substance that does not interact with normal gas. For Mund, this is a severe challenge. If gravity is simply modified, the lensing mass should be centered on the visible mass, the gas and stars. That it is not suggests there truly is something extra, something that is not ordinary matter providing the gravity. Proponents have developed relativistic extensions of Mund like tensor vector scalar gravity or TVS, which add extra fields to explain lensing, but these models become complex and lose the elegant simplicity of the original idea. The second, and perhaps more formidable, challenge comes from the dawn of time. The cosmic microwave background is a snapshot of the infant universe, and its detailed pattern of hot and cold spots is a precise record of the interplay between gravity, radiation, and matter. The standard model of cosmology with dark matter and dark energy fits this pattern exquisitely well. The acoustic peaks in the CMB's power spectrum are a fingerprint of the early universe's composition, and they strongly favor a universe where dark matter is 5 times more abundant than normal matter. Reproducing this precise fingerprint with a modified gravity theory alone, without any dark matter component, has proven incredibly difficult. While work continues on constructing cosmological models within Mund-like frameworks, none have yet matched the comprehensive success of the standard model across all scales, from the largest structures to the earliest moments. Mund stands as a brilliant and necessary rebellion. It forces us to question our most fundamental assumptions and reminds us that our theories of gravity, however successful, are ultimately models that must be tested at every frontier. It may not have won the day, but its persistence has sharpened the dark matter debate, compelling the mainstream to explain galactic dynamics with ever greater detail. In the end, the universe may contain unseen particles, or it may be governed by unseen laws. The quest to decide which is true remains one of the most thrilling battles in modern science. Mund's challenge was to build a new cosmology from a new law of motion. But what if the problem is even deeper? What if gravity itself is an illusion, a side effect of something more fundamental? This is the breathtaking claim of emergent gravity, a theory that seeks not to modify Newton or Einstein, but to explain why their laws work at all. Proposed by theoretical physicist Eric Verland, this idea pulls from the most radical concepts in modern physics: holography, quantum entanglement, and the nature of information. It suggests that gravity is not a fundamental force that exists on its own. Instead, it emerges, much like temperature or pressure emerges from the collective jostling of countless molecules. You cannot point to a single molecule and say this is temperature. Temperature is a property of the crowd. Verland proposes that gravity is the same, a thermodynamic consequence of the information stored on the boundary of space. Think of the universe as a cosmic hologram. The three-dimensional world we experience with its stars and galaxies could be a projection from a two-dimensional surface that contains all the information about what is inside, like a movie encoded on a flat DVD. On this fundamental screen, bits of information are entangled, and when you add new matter to the universe, a star, a planet, it effectively adds new information to this cosmic hard drive. To accommodate this new information, the screen must reorganize itself. This reorganization, this entropic pushback against the new data, manifests to us as the force we call gravity. It is not a force pulling you down, it is the universe's way of responding to your presence in its information network. From this radical starting point, something remarkable happens. When Verland applies his equations to the space around a galaxy, he finds that the visible matter alone, plus the presence of dark energy, the energy of empty space, generates an extra gravitational effect. This effect is strongest in regions of extremely low acceleration, exactly where Milgrom's moment kicks in. In this view, dark matter is not a substance. It is a mismatch. It is the gap between what we expect from fundamental gravity and what we actually get from gravity as an emergent entropic phenomenon. The extra pull holding fast-moving stars in galaxies is not from invisible particles, but from the way visible matter interacts with the dark energy background through the holographic information budget of space. It is a cosmic accounting error that vanishes when you use the right ledger. This theory is profoundly elegant because it ties together three great mysteries: gravity, dark matter, and dark energy. It suggests they are not separate puzzles, but different facets of a single, deeper truth about how information shapes reality. The status of emergent gravity, however, is that of a brilliant sketch. It successfully derives Mond-like behavior for galaxies, a major achievement from first principles. But a complete theory of the cosmos must also explain the bullet cluster, the cosmic microwave background, and the large-scale structure of the universe. Can an information-based approach reproduce the precise acoustic peaks in the ancient light of the Big Bang? Can it explain why galaxy clusters seem to have their mass separated from their gas? These are the formidable tests that Verland and others are now working to meet. The theory is evolving, with new mathematical formulations being developed to extend it from the scale of galaxies to the scale of the entire universe. For now, emergent gravity stands as one of the most provocative ideas in theoretical physics. It does not ask us to find new particles or to tweak an old law. It asks us to reconsider the stage upon which the cosmic drama is played. Is space-time itself the final, fundamental reality, or is it merely the screen upon which a deeper quantum truth is projected? The answer could redefine everything we think we know about the fabric of the cosmos. Emergent gravity suggests the stage itself is alive with information. But what if the stage is not just active but adaptive, changing its very properties to hide from us? This brings us to chameleon fields, a theory where the dark energy driving the universe apart is also a shapeshifter, cleverly disguising itself in our midst. The central character is a hypothetical scalar field, a kind of invisible energy fluid that fills all of space. Unlike the cosmological constant, which is static, a chameleon field is dynamic. Its most bizarre feature is that its mass, and therefore its influence, depends entirely on its surroundings. In regions of high density, like here on Earth or within our solar system, the field becomes extremely heavy. A heavy particle has a very short range. It cannot reach out and influence things far away. The field effectively screens itself, hiding its effects in the dense jungle of ordinary matter. This is why our most sensitive laboratory experiments, designed to measure the faintest forces, have not detected it. It is not there to be found in any significant way. But venture out into the cosmic void, into the vast, near-empty spaces between galaxies, and the chameleon undergoes a dramatic transformation. In those regions of incredibly low density, the field becomes incredibly light. A light particle has a long range, and its energy can exert a gentle, repulsive pressure on the fabric of space itself. This is the ingenious twist. The same field that is invisible here on Earth could be the very engine of the universe's accelerated expansion on the largest scales. It is a single entity wearing two masks. The implications grow even more fascinating when we consider gravity. If such a field exists, it would couple to matter. This means it would not just fill space, but interact with it, subtly altering how gravity works in its presence. In the sparse outskirts of a galaxy, where the chameleon field is light and far-reaching, its additional pull could mimic the gravitational effects we attribute to dark matter. Stars orbiting at the edge would feel this extra tug from the field itself, not from an invisible halo of particles. It is a compelling synthesis, offering a potential unified explanation for both dark energy and at least some phenomena of dark matter with one adaptive, elusive field. The hunt for this cosmic chameleon is a game of exquisite subtlety. Since it hides in dense environments, you cannot look for it directly in a place like Earth. Instead, you must design experiments so sensitive they can detect the infinitesimal screening itself, the tiny, residual force that might leak through its disguise. One approach uses atom interferometry. Here, clouds of ultra-cold atoms are dropped in a vacuum chamber. As they fall, they are split and recombined using laser pulses, creating an exquisitely precise quantum interference pattern. The presence of even a faint, new force from a chameleon field would minutely shift this pattern, a deviation from the expected dance of gravity alone. Another method employs torsion balances, perhaps the most sensitive force-measuring devices ever built. These instruments suspend a small, horizontal bar on a thin fiber in a near-perfect vacuum. Any tiny force on the bar will cause it to twist. By bringing a dense, spherical mass close to the balance and meticulously mapping the gravitational force, scientists can search for any anomalous extra attraction that does not match Newton's predictions, a sign that the mass is partially screening or interacting with a hidden field. These experiments probe a realm of forces so weak they are almost philosophical, yet they hold the key to understanding why the universe is tearing itself apart. The chameleon field represents a masterclass in cosmic evasion, a hidden actor that changes its script based on the density of the audience. Finding it would mean discovering that the vacuum of space is not empty but intelligent, adapting its hidden properties to remain forever just out of sight. That cosmic chameleon is a shapeshifter, but it still plays two distinct roles. What if the roles themselves are an illusion? The 20th theory proposes a radical simplification, suggesting dark matter and dark energy are not separate actors at all, but different masks worn by a single, unified entity, a dark fluid. This idea is born from a profound sense of cosmic economy. Our current standard model of cosmology requires two completely independent, unexplained components to make the math work: cold dark matter to clump and form structure, and dark energy to push space apart. It feels like a patchwork. Could the universe really be that inelegant, or is there a single, underlying substance whose properties simply change over cosmic time? Enter the Chaplain gas, the most famous candidate for this unified dark fluid. Imagine a strange, cosmic substance that acts like two different things depending on when you look at it. In the dense, crowded early universe, this fluid behaves exactly like cold dark matter. It has negligible pressure, allowing it to clump under gravity, seeding the galaxies and clusters we see today. It is the sculptor, but as the universe expands and thins out, a remarkable transition occurs. The fluid's internal pressure becomes significant and negative. This negative pressure acts as a kind of cosmic repulsion, accelerating the expansion of space itself. The sculptor puts down its tools and becomes the stagehand, pushing the curtains of the cosmos apart. In this model, the dark fluid is a single equation of state that evolves, seamlessly transitioning from a matter-like phase to a dark energy-like phase. The appeal is intoxicating. It replaces two great unknowns with one. It tells a cleaner story. The dark sector is not a zoo of different particles and energies, but a single, evolving substance whose changing character writes the entire history of the universe, from its clumpy infancy to its lonely, accelerated future. It is the ultimate minimalist's dream for cosmology. Yet, as with all beautiful ideas, the universe provides harsh tests. The primary challenge is making this single fluid behave correctly at all times. The cosmic microwave background is a meticulous ledger of the early universe. Its detailed pattern of hot and cold spots encodes precise information about how matter clumped and interacted with radiation. A unified dark fluid must reproduce this exquisite pattern perfectly. The problem is timing. To grow the large-scale structure we see, dark matter must start clumping very early while radiation is still dominant. If the fluid retains any appreciable pressure or exotic behavior during this critical epoch, it can suppress the formation of small-scale structure in ways that conflict with the observed galaxy distribution and the CMB's acoustic peaks. Getting the fluid to act like perfectly cold, pressureless matter early on, and then switch to a cosmological constant later, requires a delicate and often fine-tuned balancing act. Furthermore, observations of galaxy clusters and their evolution over time place tight constraints on how much such a fluid can fluctuate. The bullet cluster, with its clear separation of mass from normal matter, also poses a significant hurdle. A fluid that is smooth and uniform enough to drive acceleration today would have difficulty explaining the lumpy, clumped gravitational lenses we see in colliding clusters. To survive, unified models often must introduce additional complexities, like allowing the fluid to have small, sound speed oscillations or to interact with normal matter, which can begin to erode their initial simplicity. The quest for a unified dark fluid is a high-stakes gamble. It is the search for a cosmic philosopher's stone, a single substance that can transmute from the glue of galaxies into the fuel for expansion. While no model has yet achieved a perfect fit with all the data, the pursuit continues to inspire new mathematics and new ways of looking at the cosmological puzzle. It forces us to ask whether our tidy categories of matter and energy are truly fundamental, or merely phases of something deeper and more mysterious flowing through the veins of spacetime. The universe's ledger is still missing half its entries. We have accounted for all the dark matter we cannot see, but there is a parallel mystery hiding in plain sight, the missing ordinary matter. According to the precise accounting of Big Bang nucleosynthesis, the universe should contain a specific amount of baryonic matter, the familiar protons and neutrons that make up stars, planets, and us. Yet when we tally up all the stars, glowing gas, and dust in the cosmos, we only find about half. Where did the rest go? The answer may not lie in exotic particles, but in a hidden ocean of searing hot gas, so diffuse it is nearly invisible. This is the warm, hot intergalactic medium, or WIMP. Picture the cosmic web not just as a structure of galaxies, but as a network of rivers. The galaxies are islands in that river, but the rivers themselves are not empty. They are flowing with a thin, superheated plasma, a fog of ionized hydrogen and helium at temperatures of hundreds of thousands to millions of degrees. This gas is so hot it does not emit visible light, and so thin that a cubic meter of it might contain only a single atom. Spread across the vast voids between galaxies, however, its total mass could finally balance the books on the missing baryons. The clue to its existence is written in the ancient sound waves of the infant universe, imprints called baryon acoustic oscillations. In the first 400,000 years, the cosmos was a hot, dense soup of plasma and light. Pressure waves, like sound waves in air, rippled through this fluid. When the universe cooled enough for atoms to form and light to travel free, these waves froze in place, leaving a characteristic scale, a preferred distance between galaxy clusters that we can still measure today. That scale tells us how much ordinary matter was in that primordial soup. The fact that we see this imprint proves the baryons were there. They did not vanish. They simply slipped into a state that is extraordinarily difficult to see. Detecting this warm, hot haze is a monumental challenge. One method uses the universe's natural flashlights, quasars. As the brilliant light from a distant quasar travels across billions of light years to reach us, it passes through these faint filaments of hot gas. Atoms within the WIMP, like oxygen that has been stripped of 5 or 6 of its electrons, can absorb very specific wavelengths of that light. The result is a series of extremely faint absorption lines in the quasar spectrum, like a barcode imprinted by the invisible gas. Finding these lines requires immense patience and the most powerful space telescopes. Another approach is to look for the gas' own faint glow. At million-degree temperatures, the WIMP emits soft X-rays. Telescopes like XMM Newton and the upcoming Athena Observatory are designed to scan the seemingly empty spaces between galaxies, building up a statistical map of this diffuse X-ray fog. It is painstaking work, like trying to see the heat haze above a desert road from orbit. Why does this matter for the hunt for hidden particles? Because it establishes the background. Any signal from a dark matter-particle interaction in an underground detector must be distinguished not just from cosmic rays, but from potential signals caused by elusive baryonic matter. Furthermore, the gravitational maps we make of the cosmos, which we use to infer dark matter, are based on the total mass. If we do not properly account for where all the ordinary mass is, our maps of the dark matter distribution could be subtly distorted. The story of the missing baryons is a humbling reminder. Before we can confidently say we have found something entirely new, we must first find all the old stuff we already know should be there. The darkness we seek is hidden not only beyond the light, but sometimes within its faintest, most forgotten embers. Our map of the missing universe has covered ghostly waves and adaptive fields, but some hidden particles are not just elusive, they are legendary. Magnetic monopoles stand as one of the grandest predictions in all of theoretical physics. A missing piece so fundamental its discovery would rewrite the textbooks. Every magnet you have ever held, from a simple refrigerator decoration to the Earth itself, is a dipole. It has a north pole and a south pole. Cut it in half and you do not get isolated poles. You get two smaller magnets, each with its own north and south. This seems to be an unbreakable rule of nature, but in the 1930s, physicist Paul Dirac performed a stunning calculation. He showed that if just a single magnetic monopole, a particle with only a north or only a south magnetic charge, existed somewhere in the universe, it would elegantly explain a profound mystery: why electric charge in nature comes only in discrete, quantized units. The existence of one would mathematically demand that electric charge be quantized, which it is. It was an argument of breathtaking beauty, linking magnetism and electricity at the deepest level. The case for monopoles grew even stronger with the development of grand unified theories, or GUT. These are attempts to describe the electromagnetic, weak, and strong nuclear forces as different facets of a single master force that ruled the universe in its first split second of existence. In nearly all such theories, when the universe cooled and this perfect symmetry broke, it did not break cleanly. The transition would have created topological defects in the fabric of spacetime, like cracks forming in ice as it freezes. And the most stable of these defects would be magnetic monopoles. They would not be fundamental particles in the usual sense, but knots in the field, incredibly massive and incredibly stable. In many models, a single monopole could weigh as much as a bacterium, a staggering concentration of mass on the subatomic scale. If they were produced in the hot, symmetric early universe, they would be indestructible relics persisting to this day. So, could these cosmic knots be the dark matter? Almost certainly not, and for a fascinating reason. If grand unified theories are correct, they would have been produced in unimaginable abundance in the first moment, so many that their collective mass would have overwhelmed the cosmos, causing it to recollapse almost immediately. The fact that our universe is old and expanding means this did not happen. This presented a major puzzle known as the monopole problem. The most popular solution is cosmic inflation, the same rapid expansion that smoothed the early universe. Inflation would have stretched space-time so dramatically that it would have diluted the monopole density to virtually zero, perhaps leaving only one or two in our entire observable universe. They would be astonishingly rare. This makes them terrible candidates for the bulk of dark matter, but it makes finding one an event of earth-shattering importance. A single detection would be direct proof of grand unification and of the physics of the universe's first trillionth of a second. The hunt for these legendary particles is a testament to human ingenuity conducted across wildly different scales. One method looks for fossils trapped in Earth's own crust. As a heavy, charged monopole zips through rock, it could leave a trail of crystal damage. Scientists have examined ancient mica crystals, minerals that preserve such damage tracks over hundreds of millions of years, searching for the unique signature a massive magnetic charge would leave. Another approach scans the skies, the macro experiment buried deep in an Italian mountain, and its successors have used vast arrays of detectors to look for a monopole's passage, which would ionize matter in a distinctive, slow, and heavy way compared to normal cosmic rays. Perhaps the most daring hunt takes place at particle colliders like the Large Hadron Collider. While the energies needed to create a GUT-scale monopole are far beyond our reach, some theories suggest we might produce lighter, paired versions. Experiments there look for the telltale signature, a track that suddenly stops as a pair of monopoles are created and then, because they carry opposite magnetic charge, snap together in an intense burst of energy. To find a magnetic monopole would be to hold a piece of the universe's first and most dramatic phase transition. It would not solve the dark matter mystery, but it would illuminate the path that led to it, revealing that the forces we know were once united, and that the fabric of reality itself cannot into permanent, massive reminders of that primordial unity. Monopoles are cosmic relics from a unified force, but the search for dark matter has always had a favorite child. Before the deepening silence in the underground labs before the WIMP crisis, there was one particle that stood above all others as the perfect solution. It is the neutralino, the crown jewel of supersymmetry and the original WIMP miracle made flesh. To understand its elegance, you must picture the supersymmetric family portrait. The photon has its photino, the Z boson has its xeno, the Higgs boson has its Higgsino. In our universe, these are all distinct force carriers and particles. But in the broken symmetry of the early cosmos, these superpartners did not remain pure. They mixed. The neutralino is the result, a quantum mechanical blend of the photino, the xeno, and the Higgsino. It is a hybrid, a composite of the superpartners of neutral force carriers. This lineage gives it a perfect resume. It is electrically neutral, so it ignores light. It is massive, often predicted to be between 100 and 1,000 times heavier than a proton. And crucially, in the most appealing models, it is the lightest supersymmetric particle. A fundamental symmetry called R parity would prevent it from decaying into anything lighter, making it absolutely stable. A relic from the hot Big Bang, produced in just the right abundance to be the dark matter today. For decades, this was not just a candidate, it was the candidate. It drove an entire generation of experimental physics. The design of those massive, ultra-pure liquid xenon detectors deep underground. They were built with the neutralino in mind. The excitement surrounding the Large Hadron Collider was not just about the Higgs boson. A major hope was that it would produce a shower of supersymmetric particles, with the neutralino appearing as the definitive missing energy at the end of a decay chain. It was the poster child on the cover of textbooks, the central figure in 1,000 theoretical papers. The universe, however, has been stubbornly uncooperative. The LHC has smashed protons together with unprecedented energy, scrutinizing the debris for any sign of these superpartners. It has found none. The parameter space where the neutralino was expected to live has been systematically and ruthlessly carved away. The simple, elegant versions of supersymmetry that predicted a neutralino waiting just around the corner have been excluded. The direct detection experiments, listening for that faint nuclear recoil, have heard nothing but silence where a neutralino's bump should have been. The constraints are severe, pushing the possible mass and interaction strength of any surviving neutralino into narrower, more fine-tuned corners. Yet, to declare the neutralino dead is to misunderstand the resilience of a beautiful idea. Supersymmetry is a framework, not a single model. Within its vast landscape, specific configurations still thrive. One particularly clever version is the well-tempered neutralino. Here, the mixing of the superpartners is adjusted with exquisite balance, like tuning a piano string to a perfect note. This tuning allows the neutralino to have just the right relic density from the Big Bang while simultaneously evading current detection limits. Its interactions are suppressed just enough to slip past our most sensitive nets, yet not so much that it would never be found. It is a particle in hiding, not in exile. For the community that has spent a lifetime pursuing this vision, this is the ember that keeps the fire alive. The next generation of experiments with even larger detectors and higher collider energies will probe these last refuges. The neutralino's story is a lesson in scientific perseverance. It represents the hope that the most elegant mathematical answer might still be the true one, waiting for us to look in just the right way, with just the right tool, to finally reveal the shadow at the heart of supersymmetry. Supersymmetry and extra dimensions propose new fundamental particles, but the answer might lie in a different kind of complexity. The 24th theory asks if dark matter is not elementary but assembled, much like the protons and neutrons in your own body. This is the world of composite dark matter, and its most famous framework is Technicolor. The name itself evokes a powerful idea. In our standard model, the Higgs boson is an elementary particle, a fundamental scalar field that gives others mass. Technicolor proposes something radically different. It suggests the Higgs is not fundamental at all. Instead, it is a composite particle, a bound state of more basic constituents called technoquarks, held together by a new, powerful force called Technicolor. This force would be a near-perfect analog of the strong nuclear force that binds quarks into protons and neutrons, but operating at a much higher energy scale, perhaps 1,000 times more powerful. In this hidden Technicolor sector, technoquarks would combine to form technihadrons, a whole new periodic table of heavy composite particles. Among them, theorists search for a stable, neutral technobaryon. Just as a proton is a stable baryon made of 3 quarks bound by the strong force, a technoproton could be a stable technobaryon made of technoquarks bound by the Technicolor force. And this heavy, neutral composite object could be the dark matter. Its properties would be set by the scale of this new strong dynamics. Its mass would be enormous, potentially in the range of trillions of electron volts, making each individual particle incredibly heavy. And its interactions with our world would be minimal, primarily through the weak force or through the mixing of the Higgs with its composite Technicolor counterparts. This is not a ghostly particle passing through walls. It is more like a tiny, ultra-dense neutron, a nugget of an entirely different kind of nuclear matter. The detection prospects for such a complex object are as varied as the sector itself. One avenue looks for the force carriers of this hidden strong interaction. In our world, the strong force is mediated by gluons, but the residual effects are felt through particles like pions. In the Technicolor world, there would be technipions. If these technipions have even a tiny connection to our Higgs field, they could be produced in particle colliders and decay into pairs of ordinary particles, leaving a subtle bump in the data. Another approach searches for the technobaryons themselves. At the high energies of the Large Hadron Collider, it might be possible to produce pairs of these composite states. They would be electrically neutral and stable, so they would escape the detector unseen, appearing as a dramatic event with large amounts of missing transverse energy and momentum. Distinguishing this signature from a supersymmetric neutralino, however, is a formidable challenge. Perhaps the most intriguing possibility involves cosmic rays. If these technobarions make up the dark matter halo, they could occasionally annihilate with each other. That annihilation would not be a simple two-particle process, but a complex fireball of technicolor dynamics, eventually decaying into a cascade of standard model particles. This could produce unusual features in the spectrum of cosmic ray positrons or gamma rays, a messy, energetic fingerprint of a hidden strong force at work. Technicolor and composite models offer a vision of the dark sector that is not a sparse collection of lonely particles, but a bustling, complex society with its own rich physics. It suggests the darkness is not simple or silent, but as intricate and bound by forces as the luminous world we see, a mirror of our own nuclear complexity operating at a scale just beyond our current reach. The hidden complexity of composite dark matter offers a bustling society in the shadows. But what if that society exists not just in a parallel sector, but in a direction we cannot point to? Our universe might be a membrane, a three-dimensional slice of reality adrift in a higher dimensional ocean, and the dark matter could be the ripples on its surface. These are branons, particles that are not merely in our universe, but of its very fabric. Imagine our cosmos as a vast, taut sheet of rubber floating in an immense, unseen space. This sheet is our brain, short for membrane. All the particles we know and love, electrons, quarks, photons, are like tiny beads glued to this sheet. They can move freely across its length and width, but they cannot lift off into the volume above or below. They are trapped in three dimensions, but the sheet itself is not rigid. It can vibrate, it can ripple, and the quantized vibrations of this cosmic membrane are what we call branons. Each distinct ripple mode corresponds to a branon particle. They are not stuck on the brain like we are. They are excitations of the brain itself, able to propagate into the higher dimensional bulk. This fundamental difference explains their ghostly nature. Since standard model particles are stuck on the brain, they can only interact with branons when the brain's vibration directly jiggles them. It is an incredibly feeble connection, mediated solely by the tension and elasticity of the brain. The strength of this interaction is set by the brain's tension, essentially, how stiff the cosmic membrane is. A very tense, rigid brain would have high-energy, massive branons that interact more strongly. A floppy brain would have lighter, more weakly interacting branons. This single parameter, born from the geometry of reality, dictates the mass and coupling of an entire dark matter candidate. Their origin story is written in the cooling of the higher dimensional cosmos. In the fiery beginning, the brain would have been hot and quivering with violent oscillations. As the bulk space expanded and cooled, these vibrations dampened, freezing out a relic population of the lightest, stable branons. Their abundance today is a direct calculation from the brain's tension and the temperature history of the bulk. Finding them requires looking for the energy they steal. In particle colliders, when protons collide with immense energy, the debris is meticulously accounted for. If branons exist, a collision could occasionally produce one. Since it is not confined to our brain, it would immediately zip off into the higher dimensional bulk, carrying its energy and momentum with it. To detectors confined to our three dimensions, this event would look like a dramatic violation of energy conservation, a significant amount of energy simply vanishing with nothing left behind to explain it. This signature of missing transverse energy is a holy grail for many new physics searchers, and branons provide a specific geometric reason for it. Beyond the lab, we might feel their collective gravity. As components of the brain itself, branons would contribute to its mass and curvature. they would weave into the dark matter halos of galaxies, their gravitational pull indistinguishable from other candidates on large scales. However, their unique origin could leave subtle fingerprints in the way they cluster on very small scales, or in how they might interact with each other through the brain's own dynamics. The profound implication of branons is that dark matter is not something in our universe, it is a property of our universe's stage. The missing mass is not an alien substance, but the hidden vibrational energy of the reality we inhabit, a constant, silent hum of a membrane stretched across dimensions we cannot perceive. Branons are vibrations of our cosmic stage, but the stage itself might be scarred from its violent birth. Among the most dramatic fossils of that birth are cosmic strings, defects in space-time so extreme they could have woven dark matter directly into the fabric of the cosmos. These are not particles or fields, but one-dimensional cracks in reality, infinitesimally thin filaments of pure energy stretched across the universe, left behind when the fundamental forces froze into their current forms. Picture the early universe cooling from a state of perfect, symmetric chaos. As it cooled, its underlying fields underwent phase transitions like water crystallizing into ice. But just as ice forms with cracks and flaws, space-time itself did not freeze evenly. In some models, regions of the field became trapped, unable to settle into the new, lower energy state. The boundaries of these trapped regions are cosmic strings, immense, stable defects where the energy density is astronomical. A single string might be thinner than a proton, yet a single inch of it could weigh more than Mount Everest. They are scars from the universe's first moments, and they could be the universe's dark matter factories. The life cycle of a cosmic string network is a cosmic drama. As the universe expands, these infinite strings stretch and form loops. A loop once formed is not static. It oscillates violently like a whipped rope snapping through space-time. This oscillation has two profound consequences. First, it radiates energy in the form of gravitational waves. A network of cosmic strings would fill the cosmos with a stochastic background of low-frequency ripples, a permanent hum from the snapping of these primordial flaws. This is a potential target for future observatories like the Laser Interferometer Space Antenna, LISA, which will listen for the collective whisper of countless string loops oscillating across the ages. The second consequence is even more direct for our search. As a loop oscillates, it can decay, and in its death throes, it may not just radiate gravity, it could also decay directly into particles. If these particles are stable, neutral, and weakly interacting, they would flood out from the disintegrating loop like ash from a dying ember, contributing a relic population to the dark matter halo. In this scenario, dark matter is not a thermal relic from a hot soup, but a non-thermal product of the violent disintegration of spacetime's own imperfections. This theory elegantly links the invisible mass of today to the topological fossil record of symmetry breaking. It provides a potential explanation for dark matter that is entirely geometric, born from the way the universe cooled and cracked. The search, therefore, shifts from underground labs to the gravitational wave spectrum. Detecting the characteristic hum from cosmic strings would not just confirm their existence, it would open a window into the energy scale of that primordial phase transition, telling us when and how the forces of nature split apart. It would also provide a compelling production mechanism for the shadows that hold galaxies together, suggesting that dark matter is quite literally the debris from the cracking of the cosmic egg. The silence of the underground detectors tells a story not of absence but of profound isolation. While WIMP were born in the thermal chaos of the early universe and later froze out, what if dark matter was never part of that conversation at all? This is the world of feebly interacting massive particles, or FIMP, and their creation story is one of cosmic patience, not violent equilibrium. They are the true introverts of the particle zoo, so shy they never even manage to get to know the hot plasma of the Big Bang. While quarks, photons, and neutrinos were constantly colliding and exchanging energy in a frenzied thermal bath, WIMPs were on the outside looking in. They did not achieve thermal equilibrium. They were never in the mix to begin with. Their production relied on a different, far gentler process called freeze-in. Imagine the early universe as a bustling, crowded party. Standard model particles are the guests, constantly bumping into each other, dancing and interacting. A WIMP is like someone who never receives an invitation. Instead, they are created slowly, one by one, through the quiet, backdoor activities of the partygoers. Perhaps a Higgs boson, in a rare moment, decays into a pair of WIMP, or a quark and an antiquark annihilate, and instead of producing a flash of light, they produce a single, dark WIMP. These events are incredibly rare because the strength of the WIMP connection to our world is vanishingly small. But in the vast, energetic furnace of the infant cosmos, even an impossibly rare event can happen enough times to matter. Once produced, the WIMP story is simple. It accumulates. It is so feeble, so utterly antisocial, that it cannot annihilate with another WIMP even if it wanted to. There is no out for it. Once it pops into existence, it is stuck in our universe forever, drifting through the expanding space. Its final abundance is not set by a dramatic freeze out from a thermal bath, but by a slow, steady drip feed that eventually stops when the universe expands and cools enough that the parent particles no longer have the energy to create them. The mathematics of freeze-in is beautifully inverted from the WIMP miracle. For WIMP, the stronger the interaction, the more they annihilate it away, leaving fewer survivors. For WIMP, the opposite is true. The weaker the interaction, the fewer are produced in the first place. To get the correct dark matter density today, you need a coupling strength that is exquisitely tiny yet not zero. It is a delicate balancing act of profound feebleness. This very nature makes WIMP a nightmare to detect. By definition, they barely talk to our world. Building a detector to catch one directly would be like trying to catch a specific snowflake in a blizzard using a net made of chicken wire. Their signature is not a bump in a vat of xenon, it is a profound absence. Yet their creation might have left subtle marks on the cosmos. All those rare production events in the early universe, those slow decays of Higgs bosons or other particles into WIMP, would have subtly drained energy from the thermal plasma. This could have minutely affected how quickly the universe cooled, potentially leaving a faint statistical imprint on the cosmic microwave background's polarization patterns, a ghostly fingerprint of a drip feed process happening in the dark. There is another, more direct possibility on the horizon. If the parent particle that decays into WIMP is something like a meson, a particle made of a quark and an antiquark, then we might be able to create the same conditions in a laboratory. Not with a high-energy collider, but with a high-intensity beam. Experiments that slam vast numbers of protons into a target, creating copious showers of mesons, could look for a specific, impossible deficit. If certain mesons are decaying into invisible WIMP slightly more often than predicted, it would show up as a tiny shortfall in the number of their normal decay products we detect. It is a search for a whisper in a torrent, for a single missing note in a symphony of particle decays. The WIMP hypothesis embraces the silence of our experiments not as a failure but as a clue. It suggests the dark matter is not hiding from us in plain sight. It is a stranger that was only ever introduced to our universe in the faintest, most hesitant of handshakes, a shadow born from the quietest corners of creation. A particle that can vanish in a flash of light offers a way to see the unseen. For all our talk of what dark matter might be, the most thrilling evidence could come not from catching it, but from witnessing its death. This is the promise of indirect detection, a search for the aftermath of dark matter annihilation. The premise rests on a profound possibility that dark matter particles are their own antiparticles. In our world, an electron meeting a positron, its antimatter twin, results in total annihilation, their mass converting into pure energy, typically a pair of gamma-ray photons. If the same is true for dark matter, then wherever two particles meet and collide in the halo of our galaxy, they could destroy each other in a silent, invisible flash. That energy must go somewhere, and it would emerge as a shower of secondary particles we can detect: gamma rays, neutrinos, or charged cosmic rays like positrons and antiprotons. We would be looking for the funeral pyre of the dark universe. The hunt centers on places where dark matter should be densest, where collisions would be most frequent. The heart of our Milky Way is a prime target, a gravitational well where dark matter is thought to pile up. For over a decade, the Fermi Gamma Ray Space Telescope has stared at this region, mapping the sky in high-energy light. And it found something intriguing: a faint, diffuse glow of gamma rays emanating from the galactic center, an excess above what expected astrophysical sources like pulsars or cosmic ray interactions could easily explain. This galactic center excess has the rough shape and spectrum that certain dark matter annihilation models predict. It is a tantalizing whisper, a glow that seems to come from nowhere. Another compelling signal arrives not in light but in matter. Sophisticated detectors on satellites like Pamela and, later, the Alpha Magnetic Spectrometer on the International Space Station have been counting cosmic ray particles with exquisite precision. They found a striking anomaly: the fraction of positrons, the antimatter counterparts to electrons, increases dramatically at high energies. This positron excess climbs far higher than standard models of cosmic ray propagation predict. Could this be the signature of dark matter particles annihilating in the galactic halo, flooding our neighborhood with these antimatter particles? The energy spectrum of the excess even hints at the mass of the annihilating particle, pointing to a candidate several hundred times heavier than a proton. Yet cosmic detectives must always rule out the mundane before claiming a breakthrough. The universe is filled with natural particle accelerators that could mimic these signals. For the gamma-ray excess at the galactic center, a dense population of unresolved millisecond pulsars, ancient, rapidly spinning neutron stars, could collectively produce a very similar diffuse glow. Their combined emission might perfectly match the signal, a case of astrophysical confusion rather than dark matter discovery. As for the positron excess, pulsars again are prime suspects. These cosmic lighthouses generate powerful magnetic fields that can rip particles from their surfaces and accelerate them to tremendous energies, creating winds rich in electron-positron pairs. A few nearby, middle-aged pulsars could easily account for the rising positron fraction we see. The challenge is that we have not yet identified enough of these pulsars to be certain. So the work becomes one of exquisite forensic science. Researchers are not just looking for an excess, they are looking for a specific fingerprint. If the gamma rays come from dark matter annihilation, their distribution across the sky should smoothly follow the predicted density of the dark matter halo. If they come from pulsars, the map should show a clumpier, more granular structure as individual point sources blend together. Teams are now applying advanced statistical techniques to the Fermi data, trying to discern if the faint glow is perfectly smooth or subtly lumpy. The answer remains elusive, dancing at the edge of the instrument's resolution. Similarly, the precise shape of the positron energy spectrum holds clues. A dark matter annihilation signal would have a sharp cutoff at an energy corresponding to the particle's mass, while a pulsar spectrum might have a smoother, more extended tail. The latest data from the Alpha Magnetic Spectrometer is scrutinized for just such a telltale edge. This is the patient, often frustrating work of indirect detection. It requires sifting through the cosmic background, separating the possible song of dark matter from the cacophonous orchestra of ordinary astrophysics. A single, unambiguous line in a gamma-ray spectrum, or a neutrino pointing directly back to a dark matter-dense region with no possible astrophysical source, could change everything. Until then, these anomalies stand as the most compelling shadows on the cave wall, hints that we might not need to catch the ghost to see the light of its passing. For 30 years, the deepest, quietest places on Earth have been listening. They are not listening for sound, but for a touch so faint it borders on the impossible. This is the front line of the dark matter hunt, the realm of direct detection. The principle is deceptively simple. If the galaxy's halo is indeed a sea of invisible particles, then trillions must be passing through you, me, and this planet every second. To catch one, you build the ultimate trap. You descend a mile underground into an old mine or beneath a mountain, where a solid roof of rock shields you from the constant rain of cosmic rays that would drown out any signal. You construct a vessel of unimaginable purity, filled with a liquid target like xenon or argon, chilled to cryogenic temperatures and kept in perfect darkness. And then you wait for the once-in-an-era event where a passing dark matter particle, through sheer statistical luck, does not ghost through untouched. Instead, it grazes the nucleus of one of your target atoms. That tiny transfer of energy, that microscopic jolt, would create two telltale signatures, a prompt flash of scintillation light and a delayed pulse of electrical charge as electrons are liberated. Catching both signals is the golden ticket, the way to distinguish a dark matter bump from the ever-present background noise of natural radioactivity. The scale of this endeavor is breathtaking. Projects like Xeno NNT in Italy, LUX Zeppelin in the United States, Panda X in China, and Dark Side in Italy represent the pinnacle of human engineering. Their heart is a multi-ton vat of liquid xenon, so pure that the contamination level is like finding a single grain of sand in a desert the size of Texas. Their photodetectors are so sensitive they can count individual photons. Their shielding is so comprehensive it creates a silence deeper than any natural place on Earth. They are technological cathedrals built to faith in a particle no one has ever seen. And what have they heard? A silence more profound than anyone anticipated. With each new generation, these experiments have grown larger and more sensitive, pushing into realms of interaction strength far weaker than the weak nuclear force itself. They have ruled out possibility after possibility, carving away vast territories from the map of potential dark matter particles. The simple, elegant WIMP that dominated physics for decades, the one that would have shown up clearly in these detectors by now, has not appeared. Its parameter space, once a wide open plain of hope, now looks like a narrow, besieged island. This is not a story of failure, but of necessary refinement. The null result is a powerful result. It tells us what dark matter is not. It has pruned the theoretical tree, cutting away the low-hanging branches and forcing physicists to climb higher, to look deeper into the canopy of more complex, more subtle ideas. The consistent silence from these exquisite machines is the very reason we now seriously consider actions, sterile neutrinos, hidden sectors, and composite models. It is the pressure that has turned the hunt into a true exploration of the unknown, pushing us beyond the comfort of the WIMP miracle and into the wilder, more speculative landscapes where the answer may ultimately lie. The detectors keep listening, their silence a guidepost pointing us toward a darker, more elusive truth. That deepening silence from underground is a map of its own, charting where the dark matter is not. But a map is only useful if it guides you somewhere new. Our final theory is not about a particle, but about the hunt itself, a look at the astonishing arsenal humanity is now building to finally corner the mystery. The next decade will see experiments that probe realms once thought unreachable, from the impossibly light to the cosmically vast. For the lightest candidates, like fuzzy dark matter or ultra-light actions, we need to sense the gentlest tremors in the fabric of reality. A new generation of quantum sensors is rising to the task. Projects like EGE propose using atoms not as targets, but as exquisitely sensitive probes. By placing ultra-cold atoms in space in a state of free fall, They would create an atomic interferometer on a planetary scale. A passing wave of ultra-light dark matter would subtly alter the quantum phase of these atoms, a shift measurable against the silent backdrop of orbit. It is like trying to detect the faintest breeze by watching how it changes the interference pattern of two laser beams over a distance of thousands of miles. Back on Earth, networks of atomic clocks, already the most precise timekeepers in existence, are being linked together. A cloud of dark matter sweeping through such a network would temporarily change the fundamental constants of nature, making clocks in different locations tick at minutely different rates for a moment. We are learning to tell time by the shadows passing through the room. For the action, the hunt grows in scale and ambition. While Adams tunes its resonant cavity, a different approach seeks to create light from darkness. The Any Light Particle Search, ALPS II, uses a powerful laser beam fired into a strong magnetic field. The hope is that a tiny fraction of the laser photons will convert into actions, pass through a light-tight barrier, and then reconvert into detectable photons in another magnetic field on the other side. It is an attempt to shine a light through a wall using the action as a hidden tunnel. Success would be a direct, laboratory-made creation of a dark matter candidate. Beneath the mountains, the direct detection race pushes toward a fundamental limit known as the neutrino floor. As these detectors grow larger and more sensitive, they will soon face an irreducible background, the constant patter of neutrinos from the sun and cosmic rays. These ghostly known particles will create nuclear recoils that perfectly mimic a dark matter signal. To push beyond this floor will require detectors so massive, so pure, and so clever that they can distinguish the directional signature of a dark matter wind from the isotropic rain of neutrinos, or perhaps use timing and multiple interactions to tell them apart. Reaching this floor is not a defeat, it is a milestone, proving we have searched so thoroughly that only the faintest natural background remains. Our view from space is also transforming. The Euclid Space Telescope and the Nancy Grace Roman Space Telescope are not looking for particles, but for shadows on a cosmic scale. By mapping the shapes of billions of galaxies with microscopic precision, they will construct a three-dimensional mass map of the universe through the subtle distortions of weak gravitational lensing. This will reveal the dark matter scaffolding in unprecedented detail, showing us how it filaments and clusters across cosmic time. It will test whether dark matter truly behaves like a cold, collisionless fluid on the largest scales, or if the data reveals the subtle fingerprints of self-interaction or warmth. And then there is the tool that may one day untangle the theories themselves, the quantum computer. The complex interactions within a dark sector, the evolution of a universe filled with a dynamic dark fluid, or the formation of structures from fuzzy dark matter involve calculations so vast they overwhelm even our most powerful classical supercomputers. Quantum computers, harnessing the strange laws of superposition and entanglement, could one day simulate these scenarios directly, allowing us to run virtual universes with different dark matter rules and compare the outcome to our own observed cosmos. The search is becoming not just experimental but deeply computational. This is the new chapter. We are no longer relying on a single, hoped-for miracle. We are deploying a symphony of approaches, from the quantum vibrations of single atoms to the warped geometry of the entire observable universe. The mystery of the hidden particles is as profound as ever, but for the first time in history, our tools are becoming strange and powerful enough to match the strangeness of the dark. The universe has kept its secrets for 13.8 billion years. It may not keep them much longer. We have wandered through a gallery of 30 cosmic possibilities, from the elegant symmetry of supersymmetry to the radical geometry of extra dimensions. We have considered ghosts and mirrors, waves and knots, ancient black holes and adaptive fields. This staggering diversity is not a sign of confusion, but a testament to the profound depth of the mystery. The fact that our best minds can propose such wildly different solutions, each with its own compelling logic and beauty, tells us something fundamental. This is not a minor gap in our knowledge, it is a chasm at the very heart of physics, a question about what the universe is truly made of and how it truly works. Every null result from a deep underground lab, every anomalous X-ray line from a distant cluster, every puzzling rotation curve of a dwarf galaxy is not a setback. It is a chisel carving away at the marble of our ignorance, slowly revealing the shape of the truth hidden within. We do not yet know which path leads out of the dark. It may be a particle we have already imagined, waiting for a more sensitive experiment. It may be a law of gravity we have not yet written. Or it may be something so strange, so utterly beyond our current categories, that it will force us to rebuild our understanding of reality from the ground up. That is the true promise of this quest. To solve the mystery of the hidden particles is to do more than just fill in a missing component of a cosmic inventory. It is to pull back the curtain on the stage itself, to understand the fundamental script from which all light, all matter, and all force are written. The darkness is not empty, it is the canvas, and we are just beginning to see its texture. So tell me, which of these 30 paths feels most compelling to you? Is it the whisper of the action, the shadow of the sterile neutrino, or the radical revision of gravity? Share your thoughts in the comments below, ask your deepest questions, and subscribe to join us as we continue to explore the greatest mysteries of the cosmos.